Very much, everyone, for coming today. We are honored to have our guest speaker, Dr. Brownis, the Supinski.
That's Supinski.
Am I right? To our SSC seminars to give us a talk on the design of EI Capitan.
El Capitan.
El Capitan, thank you. And is there any short or ESA Exascale system? Am I right?
NNSA Exascale system.
Oh, Anna. Yeah, now I'll handle the session to you. Yeah, please start.
All right. So good morning. It's a pleasure to be here at Monash. It's actually my second time here. So first of all, El Capitan will be the next ASC ATS to be cited at LLNL. There's a long bit of, and it will be the first NNSA exascale system. So now, having given you all that alphabet soup, I'll try and explain some of it. So first of all, NNSA is the National Nuclear Security Administration, which is the part of the Department of Energy that LLNL, which is Livermore National Laboratory, it includes LLNL. So I work at LLNL. I'm the CTO for Livermore Computing, or LC. So CTO, I'll assume you know what that means. Anyway, so Livermore Computing is a supercomputing center at Lawrence Livermore, which is a DOE laboratory. ASC is Advanced Simulation and Computing, which is basically the part of the NNSA that fields the large computer systems. So that's the part that funds the part of Livermore that I work for. ATS is an advanced technology system. So that, yeah, we're cleaning up the screen here locally. So ASC has kind of two different primary lines of large systems that we deploy. Advanced technology systems and commodity technology systems. So commodity technology systems are basically standard Linux clusters. We run the TriLab operating system software on them, which is TOS, which is a TriLab project. So NNSA has 3 laboratories, Livermore, Los Alamos, and Sandia. And so the CTS get deployed at all 3 laboratories. We're currently in the process of deploying CTS2. So this second, since we named them CTS, before that they were called TriLab capacity clusters. I don't know. Politicians, they have to change names, because, you know, triple modular redundancy is pretty straightforward. Now, that costs a lot of money, so that's not what we wanted to do. But nonetheless, the predictions of failure were always kind of a little bit silly to me. Getting to things that are a little bit more realistic, one of the big concerns was how much you would need to energy and the impact on performance that you would get from having to move stuff between main memory and off to like large scale parallel file systems. All right. I think we've come up with a pretty good solution for El Capitan to that problem, and I'll be telling you more about that shortly. And then for parallelism, the issue was, in order to get to exascale systems, the predictions were that you would need roughly overall billion-way parallelism. And the issue is, how are you going to program a system with that needs that much performance, and can you identify workloads that will provide it? Identifying the workloads was done a long time ago. So it turns out that, yes, we can actually find workloads that have that much parallelism, but will you be able to program them? So I will claim that El Capitan, which we're in the process of citing right now, actually addresses these challenges successfully. if I actually go and look at the Coral 2 RFP, so Coral is the collaboration of Oak Ridge, Argonne, and Livermore, and Coral 2 was the second instantiation of an RFP under that collaboration. Sierra and Summit were systems that were deployed under the Coral 1 RFP. All right. If you've heard of Frontier, which is, the first exascale system that was deployed at Oak Ridge, that was also under the Coral 2 RFP. So that came out in 2018. And at that point, we had a little better knowledge of what we would be able to support and what we could realistically expect to have to site. So at that time, we said that the energy consumption would need to be under 40 megawatts, and that 20 megawatts to 30 megawatts was highly desired. And I'll get to why we would desire that in a minute. Now, it still didn't necessarily move away from the goal of 20 megawatts for an exascale system. Oak Ridge likes to say that Frontier takes under 20 megawatts to achieve an exaflop sustained on LINPACK. So they actually in some way made that goal of 20 megawatts. We then said, rather than specific reliability of specific components, we wanted the system to be able to run 6 days without human intervention due to failure. All right, and we think we'll make that one. That actually is proving to be more difficult than we would have hoped due to maybe the reliabilities of the software stack that you get from the vendor not being everything we would like. We then said that we wanted 8 petabytes, so binary petabytes of memory and file system capacity that's 50 times the memory, the overall memory. And we wanted to improve application performance by 50x over Sequoia. And Sequoia is the previous sort of ATS. Again, the politicians renamed this, the lines, but we've been building large systems for a while. Sequoia was a 20 petaflop Blue Gene Q system at Livermore. The reason that we phrased it in terms of Sequoia is I mentioned that this RFP came out in 2018. It was actually before we had finished citing Sierra and Summit. So in order to have baselines that we could require in our RFP, we had to compare them to an existing system. And so we were actually comparing to Sequoia and Titan. For the most part, Sequoia offered higher baseline performance than Titan at the time. Anyway, so we actually will meet most of these high-level requirements. The one we're not going to meet is 8 petabytes of memory. The original design that we contracted for with El Capitan had over 8 petabytes of memory. So in fact, Frontier has over 8 petabytes of memory. We made some design choices during the course of build, so the contract was placed basically 5 years ago in 2019. And over the course of that contract, we made some design changes that ended up reducing the total amount of memory that we get. So will be under 8 petabytes. I'll tell you a lot about the system shortly. First, I want to take a brief diversion into, first of all, looking at what we get in terms of energy efficiency, and then telling you how we prepare to actually site a system like El Capitan. And then I'll get into more details about El Cap. But anyway, so I actually went to the Green 500 and plotted out. You've probably seen this chart for performance off of the top 500. With the top 500 one, they show you the number 1 system, the aggregate of the top 500, and then the number 500 system normally. All right. I wanted to produce the same chart for the green 500, but I learned some things in going about putting this chart together about the green 500. And the first thing I learned is that they have not had 500 systems on the green 500 for most of the time of the top of the list. It's only like the last, I don't know, 3 or 4 lists that they've actually had all the way out to 500 systems. So if I took the aggregate, it wouldn't be an aggregate of 500 systems, and I couldn't put a number 500 system. It would be 0 for a large portion of it. So it wouldn't give the right details. But the message here really is that, well, and then there's also some oddities, like on the top 500 for performance, it never goes down because the system that's #1 stays there. I don't know what happened here. System went away. It sort of surprises me, but they dropped down for a while and then went back up. But for the most part, you see that the energy efficiency of systems has been pretty steadily increasing over roughly the 10 years of the list that I depict here. All right. And actually, for the most part, that's a matter of technology improvements. If you know how processors are over time, they get significantly more power efficient over time. All right. And so what we see is that it's roughly a 20 to 25x improvement over the 10 years of the list in terms of how power efficient the #1 system on the green 500 is. This is the frontier test and development system called Crusher. That is, as you can see, over actually 60 gigaflops per watt, but over 50 gigaflops per watt. The green 500 is a measure of LINPACK performance divided by the power that was required to actually generate that performance. All right. And so on LINPACK, at least, if you want to get to 20 megawatts per exaflop, you need to get 50 gigaflops per watt. All right. And so on LINPACK, at least, Frontier is actually exceeding that as it's over 60 gigaflops per watt. So that goal was made. I'm not going to tell you a huge number of details. In fact, really none. I can tell you a lot of details about how Frontier is compared to what I'm going to tell you about El Capitan. But for a variety of reasons that hopefully when I'm done here, you'll be reasonably convinced of. I expect El Capitan's power on LINPACK to be significantly better in terms of gigaflops per watt. All right. But before I go into that, I want to, as I said, go into the kind of facilities preparations, and that'll kind of really establish why this 20 megawatts for the system was an arbitrary number that I don't understand where they got it from. So we are actually expecting to need a lot more. I mean, I told you that Sierra is a roughly 10 megawatt system, and Frontier's total power is over 20 megawatts. El Capitan will be in the range of 30 megawatts. All right. So what we actually had to do, so our facility had, when we first built it, it was a 3 megawatt facility, and we built it able to immediately go up to 7.5 megawatts and then to 15 a few years later. At the time we did the RFP for Coral 2, we actually had a 45 megawatts that we can deliver to the computer floor. All right. So that would be able to handle that system. But when we deploy a system, we also keep the previous system up and running. And we actually wanted our facility to be able to handle 2 exascale systems at a time as a result. So we want to be able to deploy the system after El Capitan while El Capitan is still running. So that means that if we want to be able to handle a 30 to 40 megawatt system, we need to have over 60 megawatts that we can deliver to the floor. So we did a upgrade for the facility that took it from 45 megawatts to 85 megawatts. And this started in 2020, right as the pandemic started. So it was kind of a challenge for our facilities people, but they managed to get it done in May of 2022. So that was on time and under budget, which was really quite an accomplishment. The people who that I work with that were in charge of this part of the project really did an outstanding job. And it enables us now to actually operate 2 exascale class systems at the same time. In addition to upgrading the power, we upgraded the cooling. This is the finished product of what we called the Exascale Computing Facility Modernization Project. All right. Anyhow, so I think a lot of times people don't realize the scale of the infrastructure needed to run supercomputers. And so I'm going to just show you some pictures that show you this. So here you see the site prior to ECFM. These cooling towers here on this picture on the left of the slide, those are the same ones that are kind of in the middle of the slide of the picture on the right. Those were our existing cooling towers. And then all of this stuff, the new cooling towers are on the left of the picture on the right, and then all of the electrical infrastructure, the transformers and everything in the electrical yard there were also added. So now this gives you kind of an idea of the scale of the infrastructure that's added. Anna Maria Bailey, who oversees this project, she's the lead of our facilities team, likes to say over the course of time, we've gone from residential through commercial to now we're at utility grade infrastructure. And you can see from these people standing there that the transformers are huge. It's really quite a project, quite impressive. The cooling towers are really quite massive. These are several people standing on the top of them, so that gives you a pretty good idea of the size of those cooling towers. And then in addition, this is how we actually get it into our building. This part of the building here on the right, that's the actual computer room floor. All right, and as you can see here, this actually brings the water, the cooling water into the facility. So our facility, the computer floor is on the floor is actually on the second floor, although so it's a freestanding floor that goes the entire way. There is a wall in the middle of it that isn't a structural wall. Today when it was first built, it was designed so we could remove the wall if we needed to have a system to span the whole floor. Over time, we've actually added a bunch of electrical panels and stuff into that wall. So now we couldn't really remove the wall without making other significant changes. But over time, the systems have gotten denser and denser. So El Capitan will fit easily into the west machine room. And so there's actually room for more than El Cap up there. All right, so what is El Cap going to be? So we're getting it from HPE. It's going to have AMD processors. I'm going to tell you a lot about the AMD processor that we're getting. It's actually the MI300A APU, which is accelerated processing unit. Why is it not a GPU or a CPU? Because it's actually a single package that combines GPU chiplets and CPU chiplets on the same package. And that offers us significant advantages. What we've said so far is the system will be over 2 double precision exaflops. I find it amusing. A lot of the hyperscalers and people like Tesla and others have said, we have exascale systems, and they're talking about half precision exascale systems, which doesn't really count. All right.
Like the physicist. Down for simulation.
Yeah, but it doesn't, I mean, it's useful. I'm not saying they're not useful systems, but calling that an exascale system and saying we've met the exascale challenge. Well, no, you're at not even a quarter of the capability that we were talking about when we were saying we need exascale systems. That's why I say it doesn't really count. All right. You can roughly multiply that by 4 and get to where we'll be with LCAP. It's actually higher than that, but so it 10 to the 19th, 10 to the 18th, I don't know. It's all kind of one or the other. Like Frontier, we'll have a slingshot interconnect. So when we do these large systems, we also, in addition to funding the actual build contract, we fund non-recurring engineering activities. We jointly funded with Oak Ridge a number of activities with HPE, and some of those actually help fund improving the software ecosystem for AMD GPUs. It's still can be improved. We're continue working with AMD on that, but it's really a lot better than it was previously, and we have a lot of reasons, given that we're actually running systems already, to feel that it will meet our requirements. Anyhow, so I'm going to tell you a lot about the APU, but the first takeaway message is that it has a single physical memory that's shared by both the CPUs, the CPU cores, and the GPU resources, which will make the system a lot easier to use compared to traditional discrete GPU-based systems. In fact, that alone, our application teams are very excited about having the APU use. I'm also going to tell you about what HPE calls a near node local storage solution that we have already deployed at Livermore. It will significantly address a lot of data movement challenges in terms of access to storage. So the APU will significantly reduce data motion in order to access the main memory, which is all HBM3, and the near node local storage solution, the rabbits, significantly improve how we can interact with storage with the storage system. And I'll tell you a lot about all that. But first, more details about the APU. So it's the CDNA3 and EPYC CPU Zen 4. So the CPU cores are the Genoa CPUs, so you can actually buy Genoa CPUs. It's using exactly the same chiplets as are used in the Genoa CPU that you can buy. So that makes it a lot easier to use. We get 128 gigabytes of HBM3. Per APU, we get 24 of the Zen 4 cores. And really, we expect to save a lot in terms of power. So in order to really use a system like Frontier, which has the 8 petabytes of memory, but more than half of that memory is actually DRAM that is, physical coherence is maintained. If you want to get performance, you have to actually be from the GPUs on that system. You need to have your data in the HBM2E that's associated with the 250X GPUs. Anyhow, so this This is for those at Queensland. I know a lot of the stuff that I've done up till now has been stuff that you may have seen when I was there in July of last year. This now I get into all new material for a while. In particular, it shows you a lot more details now that the AMD is allowing us to tell people that I've known for a while about the APU. It really is a significant engineering advancement. The APU design was something that was funded under Path Forward of the Exascale computing project. So I was actually the lead on the ECP side for Path Forward, and we were very excited by generally what AMD was doing, and we're quite happy when they came to us after we'd already placed the contract and said, we're prepared to actually deliver an APU in the time frame that El Capitan is going to be deployed. It's really an engineering wonder. The IO die here really kind of the key to how it all works. All right, so that gives you a substrate that you can connect the compute chiplets, whether they're accelerator compute chiplets or XCDs or CPU complex dies, the CCDs, right? Link them all together. The interesting thing is, I have to admit that my naive assumption was that the IOD was really just kind of a bunch of wires that connect things together. It turned out that was the hardest part of making the APU work, as we learned over time. But we now are getting we have production 300As on site at Livermore. We're making use of them. They solve those problems. The really great thing about the IO die that AMD designed is that it allows all of the chiplets to have access to the HBM3 at essentially equal access, equal latency and bandwidth. So you're able to present a single unified memory address space to all of the 128 gigabytes of memory from any of the compute chiplets. So that is going to make programming the system a lot easier. I'm sure you've dealt with trying to optimize applications on NUMA-based systems, and it's a pain. I'll stop there, but you know what I mean. So yeah, I mean, there's definitely a lot of work done in terms of being able to cool the chip. And it's also like Frontier, LCAP is fully water cooled. There is no air cooling involved in the system. The what we call a capacity tier, which is essentially a traditional Lustre parallel file system. So the disks over there in that part of the system are air cooled, but the main compute system, right, all the compute cabinets are fully water cooled. So well, they had to invent special TSVs, right, to be able to connect everything together. And as I understand it, the TSVs also function in part to help with cooling. That's not my biggest expertise, I have to admit. So like the details on that, I can't really speak to as well as I would like to, David.
Just the power density going up there, right? Like
Yeah, I mean, the power density has gone up, but if you compare it to other similar generation GPUs, it's no, I mean a single discrete GPU. It's similar, right? the power requirements for, say, a Hopper GPU versus a 300A is kind of similar. They're pretty much the same. Yeah, I'm trying to think if they've released the total power on this package, and I don't know that they have. We'll see if I don't remember having it here. I will also say that there is a discrete version of the MI300 available, which is the 300X. So that's kind of similar to the 250X. As you can see here, on a 300A, you get 6 XCDs and 3 CCDs. The 300X replaces the CCDs with an additional 2 XCDs. So you get 8 XCDs. And then it's just really kind of a standard GPU at that point. So I kind of already mentioned this. This slide really illustrates the difference between Frontier's memory system and compute and what we're getting with El Capitan, which is that, with the 250X, they have fully coherent memory. So it's physical coherent. Physical coherence is maintained physically. So there's actually a tie-in between the processors so that they can actually, even a GPU can access CPU memory directly and does, actual snoops on, it gets coherence traffic. Let's say it more correctly. It's not really just a snooping protocol. For traffic from the CPU on the CPU memory, and similarly, the CPU can access GPU memory directly. So it makes it a lot easier to use, but you still have the NUMA effects, and that really makes a difference. And as I mentioned, if you want to get performance, you got to have the data located in the GPU memory. With El Capitan and the APU, we get a fully unified memory. We just get the HBM3. All right. Originally, we could have deployed additional DRAM. There are other channels, and you could design the board differently than we ended up going with. So you could add additional memory, but it would just make the system harder to use, and you spend quite a bit of your budget on memory overall. And so removing this memory actually significantly reduced the memory costs that we were paying.
Is it multiple byte, or how do you avoid racing conditions? The CPU and
Well, it's like any parallel memory system, right? So it's essentially, you're assuming that you have data race free programs, right? So if you have data races, you'll have data races, right? It doesn't matter whether I have 2 cores, 2 CPU cores accessing the same memory without synchronization, or I have 2 GPU compute units accessing the same memory, or I have a CPU core and a GPU compute unit accessing that same memory. If it's uncoordinated, it's uncoordinated, and you'll get races. So it's how you program the system. Right? I mean, it will maintain coherence, but right, like it's the classic consistency semantics, right? Like if I can basically read something from your past if
it's okay if you're running the same code in a multi-threaded multi-core process, but you've got a different code that is
it uses a unified coherence protocol. So right, I mean, so it's physical coherence maintained. It actually, the physical coherence is maintained on this system as well. All right, so a little more details about the CCD. So it's, x86, it's two-way SMT and 1 megabyte L2 for each core. They've added additional floating point formats. So like half precision, they now have bfloat 16, which if you're doing AI workloads is definitely preferable because you get more exponent bits, so you get higher dynamic range than you would with standard IEEE half precision. It's got full AVX 512. Standard memory addressability there. And each chiplet has an L3, 32 megabyte L3 that's shared amongst all the cores on a single chiplet. All right. They then connect with 3D bond pad vias, so BPVs that connect them all the way down to that IOD. So basically the bumps underneath the chiplet actually directly end up lining up with the TSVs on the IO die, and so that way you get full. That's how you get access to the underlying network that what we might think of traditionally as a NOC, although now it's a NOC that's then connected by these bond pad vias to the separate chiplets. Then in addition, as part of the IO die, there's an LLC that connects all of the chiplets on a single package. All right, and that's kind of a big deal. That's how we'll further end up reducing data motion to the HBM3. It's a pretty good sized cache down there. I think I'd say later what the actual size is, but I'll wait till I get to that. All right, and then this is the XCD that's developed new. So both the CCD and the XCD are in 5 nanometers. So it's the latest process available. So that's also pretty significant gain compared to the 250X. You get 38 compute units per XCD, 4 megabyte L2 cache shared by all the CUs, pretty larger L1 than you get with the 250X. And they didn't say how big, so I can't say either, so I won't go into that. What else here's worth going into? And then it's the same kind of connectivity with the bond pad vias, the BPVs down to the IO die.
Got a SRIOV on there. That doesn't sound like something. That sounds like something AMD would be interested in, not LLNL. Is that right?
So it turns out that the near node local storage system that we're using uses SRIOV. So actually, yes. Although it's ends up being PCI connected to that, but that part, yes. So here's some more details about the compute units. They've significantly enhanced them. I mentioned that for the CCD, they've added new formats. They've also added new formats for the GPU compute units. So in particular, this gets you again bfloat 16 here, and in addition the FP8 support. So again, it's pretty souped up in terms of AI performance, which although the bulk of our workload is currently double precision, so we care about that a lot. Our application teams are actually actively working on developing stuff that we call cognitive simulation. You can think of it as kind of surrogate models, only it's not true surrogate models because it's not a model where you expect the AI model to replace all of the physics. Instead of it's augmenting the physics with AI, where you have confidence that the AI model is going to be accurate. I think it's kind of closer to what people call physics-informed neural networks, but again, it's not strictly that, because there's still, you use a traditional physics-based model at some points, and at other points you use the AI models. Let's see. Well, the deeper instruction buffer is pretty important too to the overall performance that we expect to get. And compared to the 250X, the fact that you get twice the cache capacities is also going to be pretty significant. Some of the code teams have been L1 cache limited in terms of their performance on the 250X. Okay, so this they put in terms of 300X versus 250X performance. That I think AMD has put it out in these terms because that gives them the best, gets you a 1.7 or 3.4X improvement compared to the 250X. I said that multiply these numbers by 0.75 and you get the 300A numbers. I don't know. They didn't give me the 300A numbers to show. So I can't tell you what 0.75 times, for instance, 81.7 is, or times 163.4 is, but you can do the math. All right. And, you can easily take 0.75 and get what the comparative performance of the 300A is to the 250X. It's significant improvements comparatively. This is actually kind of what we think is more significant. So the 250X, you really only have one way that you can use the two GCDs on a 250X, which is essentially as separate GPUs. There is ways to run it as a single GPU, but it doesn't work very well because it's not really as thoroughly connected. All right. Whereas the IO die gives you enough connectivity between the different GPU dies, the XCDs, to actually run it as a single device. And in fact, the single partition is the initial way that the software is supporting on the 300A. Eventually, we'll be able to run it as 3 separate partitions. AMD uses this MPS terminology that says, okay, how many different devices do you end up using it as, in terms of how many different memory partitions do you use it as? So MPS 4 actually says that this memory, the memory is divided into 4 separate partitions, and while any of the 300X GPU, XCDs can access any of the memory on the chip, they get significantly higher bandwidth to the partition that's associated with them. All right. Originally, AMD was headed towards that direction for the 300A, but we actually didn't want them to implement it so that you get different bandwidths to different parts of the memory. So if we run it as 3 separate partitions, you get some advantages in terms of memory usability when you're running multiple processes using the same 300A. All right. But you get equal bandwidth to to all of the memory. So you still get essentially a UMA-based system, which, as I mentioned, makes it a lot easier to program. All right. So this goes into how the 300X memory system works. And again, you can just basically replace the XCD, 2 of the XCDs with 3 CCDs, and you get kind of what the 300A memory system works like. But in the NPS 1 partition mode for the 300A, you get the all of the XCDs acting as a single device still. All right. As this shows, there actually are 4 IODs, and the IODs are such that they have high speed connections between their edges. All right. And so that way, that's how you get the illusion of there being a single IOD underneath. And then here I mentioned the LLC. So it's a 256 megabyte last level cache. So that's a pretty significant improvement to the overall system, and 17 terabytes per second peak bandwidth. There you go. All right. So I included this slide because it really shows you how it all fits together and how the engineering is important here, because by just you're able to use the same XCDs, and by how you orient them, you get a single, everything fits together properly. And you do the same with the GCDs, with the CCDs. So the CCDs, as I mentioned, you can build the Genoa with the same CCDs, and that has significantly reduced the verification complexity for the overall device. The fact that we're getting reuse across multiple AMD devices, and they do the same thing with the mirroring of the IO dies. So you rotate and mirror and end up getting the same design. Allows you to build together this. Here we get actually 13 different chiplets for a single 300A. All right. And so this is what I was talking about in terms of the power delivery. Again, this is, kind of where the rubber really meets the road, that you've got the base chiplets, the IO dies. Here they call them AIDs. I won't go into why, but I don't know why they didn't change that. But basically, you've got these BPVs lining up with the TSVs and the IO die, and that's really kind of the I think the most significant piece of engineering overall in this device. Yeah. All right. Okay, so right. I'm trying to remember. All right, so the power efficiency is going up significantly. This is the comparative. So, right. So I mentioned that over time, the power efficiency of processors is going up significantly, and that's because of the clock gating that they're able to do. And so this is really trying to demonstrate that the way that this system will deliver power efficiency, so is by being able to clock gate different parts of the overall package, depending on what parts of the system are being used in a given workload. So the total power is kind of governed at one level, but by being able to say, okay, you're in a GPU intensive workload, we can allocate a lot more power to the XCDs. Or you're in memory intensive, we'll allocate a lot more power to the HBM. CPU intensive doesn't anywhere near it consume anywhere near the total anywhere near TDP of the package. So, but again, being able to move power between the XCDs and the CCDs is a significant way that the system will offer power efficiency. Now, compared to the 250, there's significant clock gating on the 250X. There's even more improvements in terms of that for the 300A. But really, I think the biggest advantage in terms of power efficiency that we're going to get with El Capitan compared to Frontier is the fact that we're not going to be moving data between the DRAM and the HBM3. But that's going to significantly improve the power efficiency over the 60 gigaflops per watt that they achieved with Frontier. All right, I think I've said most of this, but it kind of finishes things up. It does give AMD's estimate on AI performance improvements of 8x and 5x performance per watt. That roughly translates for double precision workloads, not exactly, but fairly well. And I also just wanted this final slide to kind of, again, illustrate how you have the one quadrant is CPU chiplets, and then the other three are GPU chiplets. All right, so this picture is a little bit older, but I like it, so I kept it in there. This shows AMD's Austin lab. This was about a year ago that these pictures were taken. These show the AMD single socket reference boards that they were using to initially bring up the 300A initial engineering samples. And then this shows the quad socket HPE boards that we're actually getting in El Capitan. And this gives you a nice picture of that actual blade. So in an LCAP cabinet, each so you get two quad socket compute boards per blade, so you get 8 APUs, 2 nodes per blade. You'll notice that you see here 2 APUs and then another 2 APUs that are obscured by the NIC riser cards. So now you might think, oh, so is there preferential access? No, the board's actually wired up so that there are multiple NICs per riser board, and each APU has a direct connection to one of the NICs. All right, and then as I mentioned, all of the power delivery, everything on the board is actually water cooled. So all water cooling. That's pretty significant to, again, delivering high power efficiency. But as I also mentioned, Frontier is all water cooled as well. All right, so the Rabbit program is the near node local storage solution that I've mentioned a little bit. I'm going to tell you a bit more details about that because I think it's pretty significant. Okay, I'll move faster. I will want to just cover this a little bit though. So why is it called a near node local storage solution? So this picture shows you 250X blades connected to the Rabbit module on the right. So a Rabbit module consists of 2 boards, a Rabbit S and a Rabbit P. The Rabbit S is a storage board. It's also a PCIe switchboard. All right, and the Rabbit P is a processor board that has an AMD EPIC, another AMD EPIC CPU associated with it. All right, and it also has 2 additional slingshot NICs. The interesting part for us, though, is that each of the El Capitan compute boards has PCIe connectors that connect into the PCI switch network on the Rabbit S. All right, and so then we get 18 SSD slots on again another riser card. So we can have up to 18 SSDs, SRIOV SSDs that then can be allocated either as direct node local storage for each of the compute nodes, or can be accessed as shared storage over the Slingshot network. All right, so this gives you kind of the best of both worlds. On Sierra, we have node local SSDs. The reality is that a lot of our applications aren't really prepared to make use of local storage. And so if they're accessing shared files, it doesn't work so well. And so we actually got far less utilization of those SSDs than we'd like. This guarantees us that the IO bandwidth for this near node local storage scales with the size of the system. So you get roughly a order of magnitude more bandwidth to the Rabbits than to the capacity to your traditional Lustre-based file system that we have as what we call, it's the permanent file system in a way. We can actually build transient Lustre file systems though on the Rabbits, and that's the way that we can support shared storage for our applications and deliver that higher bandwidth. All right. This gives you kind of a picture of kind of the software infrastructure. As I mentioned, you can get direct access over the PCIe to the SSDs, or you can get access through Lustre servers running on the Rabbit S, and then using Lustre clients that can then drain to the capacity tier file system. In addition, you can run containers on the Rabbit S's, so you can actually run pretty much whatever you want. And in fact, essentially, the way I like to think about the Rabbits is that they're data analysis nodes that are included in the El Capitan system. So it gives our application teams the ability to do in-transit data analysis. So it's not there's been a lot of talk throughout ECP of in situ data analysis. Now, in situ data analysis poses lots of problems because you now have you either stop and wait for your data analysis to run inside of your, accessing that's in place memory, or you have even more complex coordination issues in terms of the programming. Whereas here, you can write data to the SSDs, run something in a container. In fact, just your traditional data analysis. So we can run visit on the Rabbits, for example, which is what our application teams use for visualization and data analysis primarily. So, and actually do analysis of the data before you move it all the way to storage. We expect to get data reduction in terms of what actually gets stored all the way to the traditional file system as a result. This is a picture of an actual Rabbit unit from Livermore. So that gives you can see it's got the access to each of the SSDs without having to take the whole thing apart. Kind of important. It's also all water cooled. You can see here. So pretty nice unit. it's not something they have. I'm going to skip this, but other than to just say a big advancement for our perspective for El Capitan is it's the first advanced technology system to be running TOS, which is the TriLab operating system software built on top of RHEL, so on top of Red Hat. So it means that system administration, system management is identical to what we do on our on our commodity technology systems. And so for our sysadmin team, managing the system is, you know, not a specialized activity. It's just the same as they do on all of the other systems that we deploy. We actually have over 30 fairly significant clusters at Livermore. So we have a large data center. I'm going to skip this since I didn't get back to it. But in conclusion, as I mentioned, Frontier is under 20 megawatts per exaflop. So going back to these exascale challenges, hopefully you can see that the APU should make significant gains in terms of energy efficiency compared to Frontier. So I expect us to be significantly lower than that. In addition, the rabbits, I believe, will actually make the system much more energy efficient overall. In terms of the Green 500, you probably realize that LINPACK does no file I/O, so the rabbits will make no difference to our Green 500 number, but in terms of the actual energy efficiency of the system, the fact that we'll be able to do a lot of data reduction without having to move things all the way to the disk and before we actually do any data analysis, will actually improve the energy efficiency of the system significantly. So the Rabbit modules, so one of the things is, you know, is this whole, how long will it take to write a checkpoint, right? Well, we get a lot more bandwidth to the Rabbits than you get to a traditional file system. So that will significantly improve reliability of the system. Again, the APU design and the Rabbit modules also are going to significantly lower our data motion costs and the distance to storage. So that's going to make it so that the data motion issues that people were concerned about are really addressed a lot better. And so these are the reasons that I claim that El Capitan is successfully addressing the exascale challenges, and really the fact that we don't have to worry about coordinating moving data from CPU memory to GPU memory in order to get performance, it makes the system a lot easier to program. In fact, that's probably the thing that our application teams are most excited about in terms of what we're building with El Capitan. And that's really what I have to say, other than this is but me in front of the actual first row of the system. I think it's a beautiful picture the Livermore retiree took. So in case you're not aware, El Capitan is this kind of granite peak in the middle of the picture there. This is the Yosemite Valley in California. So that is an actual picture. Those are the actual doors of the system. We deployed them before a kind of open house that the lab had back in October. We took them back off because we're still in the process of deploying the system because we don't want to damage them. Because we only get. Actually, I think it's the most impressive system that I've seen delivered with kind of the Cray doors. I think this picture is phenomenal. We're also actually getting an unclassified system that's much smaller than El Capitan, but still a pretty significant system that we'll be calling Tuolumne. So this is kind of the main part of the Yosemite Valley. Tuolumne Meadows is if you go up to the Tioga Pass, which is the way you go from the Yosemite Valley over to basically where you can there's a little bit of California left, and then you're in Nevada once you go over the Tioga Pass. All right. Well, Tuolumne Meadows is up nice, beautiful river meadows and valley meadows and the river up by the Tioga Pass, and that's going to be that system will be sitting right here. So we'll have a nice picture of that too. It's a beautiful aspect of California that you'll be able to see. Huh?
There are cheaper ways to get a picture of Yosemite.
But not at the same scale. That's true, I suppose. But we think it'll be a beautiful system, and our application teams are really excited. With that, I'm happy to take any questions that anybody has. So what I can say is that the Coral 2 RFP said that the budgets for the individual systems, I mean, again, it said a total number, but you can easily do the math and identify that the total procurement is roughly $600 million US. All right. Not all of that's for LCAP. All right. So I mentioned that we funded a fairly significant amount of non-recurring engineering that improved what we're getting, but also what's available on the market from HPE. A lot of that also funded improvements to AMD's software stack, as I mentioned. So that accounts for a fair amount of dollars. I don't think we've announced how much gets put where, but it does. We also got several early access systems. So we have 3 relatively small systems, interesting, that are ES3 systems that are sort of mini frontiers. We have a slightly different node than Frontier, because Frontier has node local storage, whereas our ES3s have rabbits. So where we're getting early experience using the rabbits. We have a 24 node system, a 32 node system, and a 40 node system. The 40 node system was, so all 3 of those systems are in the top 200. They're between 100 and 200. I forget the exact numbers. And when they debuted, they were the 40 node system is just over 100. So it shows you just how powerful these nodes are. And we got a couple other early access systems as well as part of it that came well earlier than the EAS3 systems. So 600 million for a lot of stuff. But the bulk of that is for LCAP. I think I can safely say that.
Questions from online.
Okay.
Yeah.
So yeah, the Green 500 includes all power to run the system. So it's essentially wall power. So it's the network, the compute. I don't believe it includes the cooling. No, it's warm water cooling. So ECFM, it's all passive radiated. Yeah. So those cooling towers, have baffling in them, and you just basically the water goes down over it. I mean, it's complicated engineering, but it's passive cooling. So no, it actually, the water at Lawrence Livermore comes from the Hetchy Reservoir in Yosemite, or it's actually just outside of Yosemite. So there was the Yosemite Valley, and then there was the Hetchy Valley, but now there is no Hetchy Valley. There's the Hetchy Reservoir because they built a dam there. That happened many, many years ago. So all of that water comes down. It's the water. So the Hetchy Reservoir is where San Francisco gets all of its water. It goes right by Lawrence Livermore, and somehow, I don't know how this works. Nobody else gets Hetchy Reservoir water besides San Francisco and basically us. I'm told it's really good water. It has very low ion content, so it actually does a very good job at cooling and heat transfer. So,
It's closed cycle.
so it's there's a primary and a secondary loop. All right. So the Hetchy Reservoir water goes through our systems and then goes into our building, up through the floor into CDUs, cooling distribution units. There's one CDU for every 3 compute cabinets. The CDU then runs, so in our system, PGW, which is a good thing because PGW is not friendly to microbes. Not absolutely deadly to it, but compared to most water mixed solutions that people use, say for instance the one that they use in Frontier, it's a lot less friendly. So we'll have much less issues with microbial growth. But so our main loop goes into the CDUs and back out, doesn't go in through the compute nodes. All right. And instead that's,
It's a closed.
yeah. So the secondary is a closed loop. The primary is open. And in fact, as I said, I mean, it's, open to the air. The initial deployment, as before we've added the compute blades to the system, it was only just using the reservoir, not using the actual towers. So we get actually a fair amount of cooling just from that. It's got a lot of water in it.
Yeah, I don't understand. So you'll be pulling power out of a reservoir and running it through the cooling towers. You won't put water back into the supply. It would just be.
No, it runs back out to. Pardon?
Why cool it? If you just mix it back into the stream going on to San Francisco, it's like.
No. It doesn't go back out into the canal, but it all, right, like it comes out of the cooling towers, through the piping, into the building, up through the CDUs, and then back out, pours down the top of the cooling towers and back in.
So how much water is it using?
I forget the exact
No,
number.
well, it
It's-
wouldn't make any sense anyway. In gallons, wouldn't it?
Yes, it's an amusing thing, and I'm forgetting the exact number, but it is amusing because our facilities people talk in gallons, and the HPE people talk in liters, and there's this, and they also talk in centigrade or Celsius, and our facility people talk in Fahrenheit. And when they first started coming to them and saying, we want 32-degree water, they were like, didn't you understand that we're giving you W3 water, which is, basically up to a little over 90 degrees Fahrenheit, so it's actually up to 36 degrees C. So they're like, you're not getting. And besides, 32 degrees C water is not ice. Does that really flow? How does that work? I don't know.
So how often, aside from a impact test during commissioning, would you use all of the compute for one task, one application program?
So I don't have the chart that we've put together for it, but we've looked at jobs over our last few I'll say advanced technology systems, although again, that name change. And so El Capitan and our other ATSs are tri-lab resources. All right. So that means that they're shared between Livermore users, Los Alamos users, and Sandia users. All right. And we have the first and most important way for scheduling the system is a kind of political process, maybe I can say, called the ATCC, Advanced Technology Compute Campaigns. And that basically divides the resource up 1/3 between Los Alamos, 1/3 Sandia, and 1/3 Livermore. Roughly 50–60% of the jobs are then at roughly about 1/4 to 1/3 of the system. Somewhere around 5 to 10% of our jobs on the big systems are full system jobs. So, given the political allocation of the system, I think you could say somewhere in the neighborhood of 70 to 75% of the jobs are, full system jobs in some sense.
Should you kind of talk about what science they're doing, because that's what you're secure, right?
Well, I mean, yeah, I mean, I'm not a physicist, so I kind of know, but I wouldn't want to go there because then I might get somewhere where I'm not supposed to get. I mean, what we do is not so the ASC program is the descendant of Advanced Simulation and Computing Initiative, which was started when they were putting together the Nuclear Test Ban Treaty. All right. And the idea was, okay, we're going to stop doing nuclear testing. So the US was one of the main organizers of the Nuclear Test Ban Treaty and then never signed it. Politics again. But nonetheless, we have actually operated as if we had signed it. We have not done nuclear tests in over 25 years, I think over 30 years at this point. And so the question at the time was, well, how you've got these systems, nuclear weapons, how do you know that they're safe and reliable? And so our systems are used to certify the US nuclear stockpile and say that it will work as intended. So there's a lot of different issues like in materials aging. So there's a lot of material models and there's a lot of simulations of the actual devices to understand how they would function. Then I also mentioned
Brownies, I think we need to cut here, stop here.
okay.
Yeah, also you can send like emails to Brownies for further discussions. I think, anyway, let's thank our speaker. Thank you very much.
We could take a lot. I'm gonna manage flower year round.
Yeah. We used to summit.
Hmm?
We used